The next presenters come from company emotas, embedded communication. They want to highlight one topic that had been visible also on the previous presentation. How can I migrate from a classical CAN-based system to a CAN FD-based system? So the title is Migration from Classic CANopen to CANopen FD. And it's going to be presented by Alexander Philipp. Alexander Philipp studied electrical engineering and communication technology at the Leipzig University of Applied Science. During his more than 15 years experience of development of CAN and CANopen protocol stacks, Mr. Philipp joined emotas embedded communications in 2015 and is in charge of the development of most of the CAN-based protocol stacks like CANopen, CANopen FD, J9039 and UDS. Mr. Philipp also participates in CAN automation and is the chairperson of the IG CANopen FD. So Mr. Philipp is assisted in his presentation by Torsten Gedenk. Torsten is co-founder and managing director of emotas embedded communication GmbH since 2012. He studied electrical engineering at the University of Applied Science in Mittweida, Germany, and graduated in 2003. Since 2003, he is involved with CANopen, and he was speaker at the International CAN conferences in 2008 and 2017. Besides this, he's active in various CANopen and CANopen FD standardization groups and a lecturer at CANopen and J9039 seminars offered by emotas. So much with regard to the introduction. We are keen on listening what you want to share with us. So migration from classic CANopen to CANopen FD, please, the stage is yours.
Thank you very much. And I'd also like to welcome you to our presentation. I will explain something about the migration from classic CANopen to CANopen FD together with my colleague, Alexander Philipp. Well, at first, I will say something about the company because I assume that emotas embedded communication is not that well known like the companies we've seen before. So there will be a short slide about what we are doing. Then after that, I will give you a brief introduction into CANopen and CANopen FD. Well, I assume that most of you are familiar with CANopen, so I'd like to highlight the differences between CANopen and CANopen FD. And after that, my colleague Alex will explain the migration issues, and he will present some solutions for device manufacturers and for network installations. And at the end, I will present our CANopen FD Starterkit, which is a good way to start the migration to CANopen FD. Well, the company emotas embedded communication was founded in January 2012 with a slightly different name. And since then, we are a member in CAN automation, but I and most of my colleagues already worked with different working groups and the CAN automation before that. So I personally deal with CANopen since 2001. And besides active with CAN automations, we also work with other standardization groups like Energy Bus, for example. And already in 2017, we offered the first CANopen FD stack. So it's available for a few years already. And well, the company was renamed to emotas embedded communication GmbH in September 2019. And we at emotas provide protocol stacks, tools, and services and bootloaders for various CAN and CAN FD based protocols. So we not only support CANopen or CANopen FD, but we also offer solutions for J9039 and other protocols. And as we have heard before, also with J9039, there's a migration path from classical CAN to CAN FD, and is similar with ICDP and some other protocols. Well, yeah, let's start with a brief introduction into CANopen and CANopen FD. Well, obviously it's a network based on CAN and CAN FD, and CANopen or CANopen FD provides standardized communication services. That means there are standardized ways to communicate with certain devices. There are ways to read and write parameters, to configure devices, and there are standardized ways to send signals, receive signals, or even complex tasks like a firmware update is standardized in CANopen. And besides these standardized communication services, CANopen and CANopen FD provide or may provide some standardized device functionality. So with CANopen, we have various device and application profiles, which in addition to the standardized communication services, also define a standardized communication behavior for specific devices, of course, according to the device profile. Well, CANopen isn't new, so it's very mature. It has already been published as the first version in 1995, and well, there are a lot of, or millions, or maybe more than millions, and CANopen devices are out there in the market. And the CANopen FD specification was published 4 years ago now, and there are not that many CANopen FD devices yet, but we all hope or expect that there will be more soon. Just to have a look on this slide, the gray boxes shall be CANopen or CANopen FD devices, and here I'd like to explain that CANopen or CANopen FD devices on the application level, if they communicate on the application layer, they exchange CANopen objects. And the CANopen object can be a single Boolean value, or it can be a 16-bit or 32-bit wide parameter or signal, or it could even be a longer string, for example, like a device name or manufacturer name, which is maybe 10 or 20 bytes long, or even a complete firmware of a CANopen or CANopen FD device can be a single CANopen object. And well, these objects may be longer than the 8 and or 64 bytes, which are the maximum payload of the CAN or CAN FD frames. And though the CANopen or the CANopen FD specification defines how to transfer these CANopen objects in CAN or CAN FD frames, and well, as CAN and CAN FD frames are slightly different, the representation of these CANopen objects in these CAN FD frames are different, and these differences well, will cause the migration issues in the end. Well, I'd like to focus on the most different or the most important differences between CANopen and CANopen FD. Well, obviously it's based on CAN FD with higher bit rates and longer messages with an increased payload. And CANopen FD makes use of the improved features of CAN FD and used the CAN FD features to update or improve the communication services. The three most important ones are the USDO service. In classic CANopen, you have an SDO service which is able to provide a read and write access to all objects in the object dictionary. And well, it's used for many years, but the idea was to replace it completely with a new universal SDO service, which provides much more features, which I'm going to explain on the next slide. Then, of course, we have longer PDOs in CANopen FD. We can just, the principles of the PDO are the same as before, but we've just taken, the PDOs have been just extended or can now use longer CAN frames up to 64 bytes. And the emergency message service has also been changed with CANopen FD. That means an emergency message can now contain much more information than in classic CANopen. In classic CANopen, well, most or nearly all devices or device manufacturers use EDS files, electronic data sheets, to describe the CANopen device. There was already an XML-based device description format for classical CANopen devices, and I had already spoken about the XML device description at the iCC in 2008 in Barcelona, but unfortunately nobody was using the XML-based device description for CANopen devices. But now we have reduced the XML-based device description a bit, and it's mandatory for CANopen FD devices now. Well, let's have a detailed look into the three communication services I had mentioned. The USDOs, instead of classical SDO services, now uses longer FD frames. So, and for example, previously with a classic SDO, the so-called expedited transfer was only able to transfer 4 bytes of payload because of some protocol overhead in the beginning of the frame. And now with USDO, a single expedited transfer can transfer up to 56 bytes of payload in one CANFD frame. And so the expedited transfer covers most of the objects in the object dictionary actually, but there is still, which isn't shown here, but there is still a segmented transfer for larger objects, and there's also a bulk transfer with USDO, which is a bit similar to the block transfer in the past. But the new, or the one of the most important things with USDO is that now the UST service provides a possibility to broadcast transfers to all nodes in the network, and the routing to other remote CANopen FD networks is now integrated in the USDO protocol itself. But maybe the most important change is that now a direct USDO communication between two devices is possible without any configuration efforts. If you know classic CANopen, you will know that a classic SDO communication required a pair of CAN identifiers which had to be defined in advance so that two devices can communicate. But with USDO, it's now possible to just, if the device is capable of sending USDOs, it just is possible now just to address a single device and send in USDO to it. I think there was one presentation yesterday that mentioned that there are 17 different USDO transfer modes. But today I only want to use this single slide to show how an expedited transfer works, and I would just like to focus on the differences to classic CANopen. One difference is that the USDO client, the device which initiates the USDO transfer, uses a specific CAN ID which depends on its own node ID. So the source address of the transfer, so to say, is specified in the CAN ID, and the destination address, the address of the server it wants to communicate with, it's indicated in the first byte of the CANFD frame. So any device uses its own CAN ID to initiate in USDO transfer, and the server receives it based on the destination address given in the CANFD frame. And another difference with compared to the previous SDO service is that we now have multiple sessions in the USDO service. Well, it is more important for segmented transfer maybe, but now you can have multiple sessions in parallel from one USDO client to another. This is what I just like to mention about the new features of the USDO services. And well, I had said that CANopen uses longer PDOs, and well, on this example here on the top, we can see the 4 predefined received PDOs of CIA42 drives, and well, there is a set of PDOs defined which combine the control word, for example, and some other information in various PDOs, but due to the limitation of classical CAN, it wasn't possible yet to put just or to send just the complete information in one PDO, but with CANopen FD, we can use PDOs up to 64 bytes, and it's you can just put more payload into a PDO, and it's also easier to synchronize the data on the receiver side. But well, why I'm showing you this of course these longer PDOs may cause migration issues which we have to address later on. And well, the last CANopen FD service which has been changed or improved and which I want to mention is the emergency messages, the emergency service, which provides a way to signal errors or warnings or alarms in a defined way. And historically, in classic CANopen, the emergency message only consisted of 8 bytes. And this 8 byte had been the emergency error code, the value of an error register, and 5 manufacturer-specific bytes. These 8 bytes altogether are still part of the new emergency message in CANopen FD, but now the emergency message contains 20 bytes, and there are a lot of additional information. Historically, there was a problem that different device profiles or different specifications had been able to specify the different emergency error codes, and now it's still true, but now you can add the information from which specification the error code originates. Additionally, if one have multiple logical devices, you can specify the number of the logical device inside, and you can also add additional status information about the error itself, and most importantly, you can add a time information, so the consumers of the emergency message know when the error had happened. Well, this was just a summarize of what is different with CANopen FD. And now I'd like to hand over to my colleague, Alexander, who will discuss migration issues and offer and provide solutions.
Thank you, Torsten. Yeah, before talking about solutions, I want to talk about some migration issues which could occur when migrating to CANopen FD. And of course, there are some you have to solve. First of all, the most important thing is the incompatibility of the data link or physical layer. Classical CANopen devices cannot exist in a CANopen FD network if the CANopen FD devices are using FD frames, because they are not compatible. So the classical CANopen device would destroy messages and at the end of the day destroy the bus. So they cannot run in the same network. Another issue is actually that the bit timings of FD devices have to be very accurate. It has to do with the faster bit rate they can use for the data, because they're switching in a defined point in a bit, and this defined point of the data switch or bit rate has to be very accurate, otherwise the network wouldn't work. And it's a recommendation, pretty much a strong recommendation, that all devices in a CANopen FD network use the same CAN clock. So the base for the CAN controller, the CAN clock, should be the same in all devices. And all the devices have to use the same sample point. So in classical CANopen FD, in classical CANopen network, it was possible that the sample point slightly differs, but it's still working. Okay, in the application layer, as Torsten already mentioned, one issue is the longer PDOs in a CANopen FD network and the higher bus load you can actually create. So the bus traffic could be much higher than in a classical network. Another migration issue on the application layer or on the CANopen side is the USDO with broadcast, which doesn't exist actually in a CANopen, a classical CANopen network. So you have to overcome this problem and translate it somehow. Okay. Next topic is the solutions for device manufacturers, what they could do. One solution for device manufacturers who want to make their device at least CANopen FD, let's call it tolerance. You have the possibility of so-called CAN-FD shielding transceivers. The good thing about this is you can just replace the transceiver. The bad thing is the hardware has to be reassembled, at least for the transceiver. Another issue with that is actually that the host controller or the manager, the CANopen manager or the whatever, has to support both protocols, SDO and USDO, and has to have knowledge if this is a CANopen device or this is a CANopen FD device and use the right service, communication service for these devices. Some proposals for CAN-FD shielding transceivers come from, for example, Quasar, NXP, and others. And an exact product is, for example, the NXP TGA 11145, which is just, they have a so-called CAN-FD passive mode. If you are creating new devices, then a good solution would be that you create a device that it supports both CANopen and CANopen FD. How do you can achieve that is simply by using an CAN-FD capable CAN controller or hardware, which is available since several years from many semiconductors, and also use a CAN-FD capable transceiver. And then on software side, you can use CANopen or CANopen FD stacks that allow the selection of the protocol, so CANopen or CANopen FD, for example, at startup. So that you simply by configuration can run as CANopen or CANopen FD device. Another solution could be that you use CANopen to CANopen FD bridges, which, yeah. Next topic I want to talk about is solutions for network installations. Solutions for the migration issues on network side is use CAN-FD SIG transceiver to simply improve the signal quality and keep the old, let's call it the old network, the old topology usable for higher bit rates. Another solution could be partial networking, where you, for example, disable the devices or put them to sleep, which are only supporting CANopen, and then talk to the devices which support CANopen FD. And when you're done with it, for example, when you're doing a firmware download or something like that, then you wake up the classical CAN nodes again, and then you just communicate with CANopen, classical CANopen. Another thing which was also in the speech yesterday is to use gateway and bridges, which connect separate networks into classical and FD segments, and then somehow do the translation Yeah. Our preferred solution, or our solution, is actually the so-called CANopen FD proxy software, where you can simply, which includes pretty much CANopen FD device and classical CANopen manager. And this proxy or gateway emulates multiple connected classical CANopen devices, emulates them in the software as an CANopen FD device. So you can connect the FD side to the FD network, and we would act actually as an CANopen FD device in the FD network. And the good thing is about this, that the manager on the FD side, for example, doesn't even know anything about that it's actually not a real node and not an FD node. It's just talking to it just the way before, and then the proxy software translates the different services, like the USDO server. It translates it to an SDO client. We will see it on the next slide later on, so that the FD side doesn't see any difference. It supports PDOs in both directions. It has NMT and heartbeating forwarding in both directions. It has emergency routing for CANopen to CANopen FD. Of course, as Torsten showed in a slide, we are losing some information. Not losing is the wrong word. On the FD side, the emergency is a little bit longer, and we don't have this information. We only have the 8 bytes, which are on the CANopen side, but anyhow, it's better than nothing. And we already created a proof of concept implementation, and it's available for CAN4Linux, so as a Linux software, and on the STM32G4. And this is a very simple example of our proxy software. So the gray box in the middle is pretty much the software. On the right side, you see the CANopen FD network with 3 nodes, 4, 8, and M. M stands for manager. And on the left side, you see the classical CANopen network with 3 nodes, 1, 3, and 5. And what the proxy software does is, on the classical side, it emulates this manager from the right side for each single node. On the right side, it emulates the classical nodes as an FD node, so the manager doesn't even see a difference. And all the magic pretty much from the proxy software happens inside this gray box. So the software logic is actually translating the services, which are the red dotted lines, in each direction. There's a little bit more complicated setup you could use, which is also in the proxy software, where you have only one manager in the CANopen network, which talks to all 3 at the same time. And why I say it's more complicated, when I go back to the the previous slide. With this solution, you can actually really easy set up this proxy software, and the configuration is the emulation of the single nodes by just creating the nodes via an EDS file from the classical nodes and the XML file from the manager, and then you just use that, and it's a one-to-one translation. In the more complex solution, your software, your proxy software, application software, has to be a little bit more smarter, because it has to handle all 3 of them and at the same time. But the good thing is you need less resources in terms of CAN ports, pretty much, classical CAN ports. Okay. The next issue you have to overcome is, if you're doing something like this and use networks, you of course need a tooling which supports both CAN FD and CAN at the same time, would be appreciable. This is an example of our tool, which supports multiple interfaces at the same time in the same window, just as in the lesson before. So you can actually see all the different networks in one window and compare and see what happens at the time. So in this red box, you see which interface actually that the message was originated or received. So 2 and 1 in this case. Another good thing you could use, or if your tooling has some kind of interpretation, because you don't want to fiddle with raw CAN messages and then count out bytes and look up in the specification what it means. And so, yeah, pick a tooling which does some interpretation, some good interpretation, just like here, where it can actually interpret the raw CAN messages and translate it into a human readable format, I would say. So in this case, you can actually see that the tool is telling me that this was an USDO on this line and an SDO on this line. And in this example, this is a real example of the proxy software. You see that somebody wants to, let's call it read by a SDO on a node, which is node ID 65 wants to read on node 16. And then the translation is done in the proxy software to the classical SDO. And when it's done, it's creating a response. So you see USDO again, 16 to 65 with the response. And some tools also offer the possibility that they actually have knowledge of the single devices via EDS files or XML files or whatever. So it actually can interpret also the content more or less. So what we see here is this is actually the answer from an SDO. The source was 16, the destination is 65. It is the CANopen object 5000, subindex 0, and the content or the payload says this is the long string. So what we actually read is a string, and in the string there was this is a long string. So multiple channel analyzers and would be a good choice to do something like this. Okay. Another example here is how you can translate PDOs. The simplest way is if you stick to the 8-byte PDOs, if you have a classical CANopen device in the network, even if it's emulated. You could use longer PDOs for all the other devices, but 8-byte PDOs would be sufficient for the classical nodes. And then you don't have to do a translation at all. As you can see here, we have one PDO sent out on the line 2, and it's just translated. Let's call it, we change the data link layer, nothing more, to classical CAN, and then send it out on the classical side, and the classical node can receive it. That's the easy way. Then you actually don't need any special configuration, and you can just work with the EDS and XML files. A more complex thing is if you have, for example, a manager who's sending out a longer PDO, which is possible with CANopen FD. Then you have to do some configuration, it's not enough to just use EDS or XML files. Then you have to divide up this longer PDO, maybe in multiple PDOs. Maybe you don't need this, you need only 8 bytes. But if you need all the data, then you have to somehow decide how to divide up this PDO. And then you have to do some configuration, of course, in the proxy software and or in the classical CAN devices, CANopen devices. So in this example, we took a long PDO, which comes from a FD device, and we divided it up in 3 classical CANopen PDOs.
Thank you. And I will go on, and I also like to show you our CANopen FD Starterkit, which is a good way to start with CANopen if you haven't with CANopen FD. So our CANopen FD Starterkit combines all hardware and software which you need to start with the CANopen FD development. So the besides a fancy green box, it comes with an STM32 G4 microcontroller on a Nucleo board. And there is, of course, a CANFD interface which you need, and cables and termination resistors. And on top of the Nucleo board, we have an extension board with a CANFD transceiver and a PDSAP9 connector, so you can connect all the components smoothly. And well, this is all your hardware. You just need to start with your CANopen FD development. And well, there's also some software required. And so our CANopen FD starter kit also comes with a free evaluation version of our CANopen FD slave stack. Actually, it is available for download. So if you already have this board, you could just download the software and put it on the microcontroller and run it. And of course, the CANopen FD starter kit also comes with demo versions of our CANopen and CANopen FD tools. So you have had everything to start with a CANopen FD the development. So, well, basically, if you start with a CANopen FD development, you need the right hardware and the right software and the right tools. And I'd like to just mention our CANopen FD tool chain here. Well, this in the middle shall be a microcontroller where you can run a CANopen, our CANopen FD stack, which handles the CANopen FD communication. And if you want to do a firmware upload or download via CANopen FD, we also offer a CANopen FD bootloader and a couple of tools around. So it's not sufficient just to have a CANopen FD stack, but you also need a set of right tools to work with them. And the tools should obviously support CANFD and CANopen FD. And well, we have a tool called Device Designer, which we use to define the object dictionary. So basically using this tool, one defines the object, one plans to use, or you can also import existing EDF files if you want to migrate an old device to a new one. And based on the definition of the object dictionary, the CANopen Device Designer generates a representation of the object dictionary. It has to be linked together with the CANopen stack and your user code to build the application. And this tool also generates an EDS or XDD files, which describe the object dictionary of the devices. And well, in order to monitor or to interpret the CANopen messages, you could use our CAN interpreter, which is able to do the interpretation of CANopen or CANopen FD messages. And we also have a tool called CANopen Device Explorer, which in addition to the functionalities of the CAN interpreter, it also acts as a CANopen manager tool. It provides USDO client functionalities, PDO producer and consumer NT producer, and so on. Well, if you want to do a firmware update, yes, we also have the dedicated tools for CANopen FD firmware download. And as a final step, if someone wants to design a complete new CANopen FD network, we also offer a tool called CANopen Network Designer, but that would be a different topic here. Well, I'd like to thank you for the attention, and I hope that we have provided you with some ideas and solutions how you could migrate from CANopen to CANopen FD. It's not easy, but it can be using the right ways. It could be a bit more easier, of course. Thank you. Bye.